So, without further ado, I'd like to introduce Bailey Hayes, who is the technical steering director of the Bytecode Alliance, the WASI subgroup chair, and the CTO of Cosmonic. So, Bailey, take it away.
Thank you, Brooks. Glad to be here. Really excited to see so many faces joining us for the first time with WasmCloud. I wanted to start the day off by talking about some of the problems that we're looking to solve with WasmCloud. And that begins with some of the pitfalls in modern platform engineering. Um, to start, we kind of need to define platform engineering. So the platform engineering as a practice really began during the containerization era and the epoch of compute, where first we started with microservices, we bundled those into VMs that allowed us to build out data centers and eventually moved to the public cloud. But really, there was this major paradigm shift that happened when we were able to package our applications into a container and then orchestrate those containers with Kubernetes. And that allowed infrastructure teams to evolve, to be part of the team that's providing a platform and giving common application services like capabilities from secrets management to authentication and authorization that then application developers are able to build on top of. And really, this was a massive improvement in our productivity and the types of things that we're able to build, but it does come with some pretty big problems. Namely, that building applications today are just too expensive to build, maintain, and run. And that really starts with the initial application language choice. And using that app effectively template that we build for all of our different apps across enterprises, we are tied into specific clients and frameworks that are part and built for that language. And we have to maintain these apps on an app by app basis. The platform engineering teams are usually on the hook for the application platform layer here. That's all of the authentication, observability, maybe even artifact registry, secrets, common storage layer, messaging, and more types of capabilities. And for the application platform team to be able to evolve their platform, if they are trying to make a new API level change, moving to a new major version, application developers have to update their dependencies, but they're not just revving for being able to evolve the platform. They're revving because most of our application code is not our code. It's full of open source code, which is actually a great thing. It's amazing that we're able to do this. However, that comes with a significant cost and burden on maintaining your application code to prevent vulnerabilities. And so both by having boilerplate code for your platform and for open source dependencies, we're constantly churning on this application like hamster wheel of building apps. And we don't really have an easy way to wrangle that problem. And now on the running and deployment side, platform engineering teams are stuck managing these very expensive platforms. Typically, it's built on top of Kubernetes today as the orchestration layer, and it really lacks portability because it doesn't allow us to run in many different types of environments like on the edge. So throughout this platform evolution that we've seen, moving through the public era, including containers as part of that era, but that being the major paradigm shift, I believe that today we are now in a new componentization era, where our new next unit of compute is WebAssembly Components, and that's orchestrated by WasmCloud. So let's take a step back and just do kind of a basic comparison between Wasm and containers. You can think of Wasm as perhaps a tiny VM, so this type of direct comparison works okay. Containers themselves are much larger. They're usually in the order of megabytes to gigabytes, whereas a WebAssembly component is in kilobytes or megabytes. WebAssembly components themselves are secure by default. For containers, we have to add a number of processes, best practices, and tools to get them to a place where they are secure and provide the right level of isolation. But they're still not generally considered the right choice when you're trying to run arbitrary user code, and certainly not on a user's device. Now, the other difference here, while containers give us much more new layers of portability, those images are still CPU architecture bound. Whereas WebAssembly components, this .wasm, it doesn't need to change for any different environment, so long as that environment has a WebAssembly runtime for it. But perhaps the most important difference between containers and components is that containers start in seconds, whereas WebAssembly components start in less than a millisecond. And that really enables WebAssembly Components to solve this major problem that we have in the industry, is that it solves the cold start problem. Containers, because they take several seconds to start, they have to keep effectively a pilot light on. They have to keep many different containers running, even though they're not necessarily servicing any requests, because when you get a burst of requests, it takes seconds to scale out. And your response time that a typical user expects is less than a second, so you can't wait on a new container to spin up. Compare that with a WebAssembly component. This list of numbers here, these are numbers that every programmer should know. You've probably seen this set of numbers before, but I think it's really important to highlight where WebAssembly components fit into this latency story. WebAssembly components, because they start in less than a millisecond, it means that it's so much faster than even making a network request. And so you're going to see new types of architectures evolve because of this new layer that WebAssembly components fit in. Why make a network request to somewhere else when you can be running that compute on the edge next to the user? Now, with every new unit of compute, every new thing that we're distributing around, you need a new orchestration layer for that. And that's what WasmCloud is. It's a Wasm native orchestration. It allows you to deploy and manage your Wasm applications across any device, cloud, or edge, including your own. Now, when we're building a WebAssembly component, you get a new way of simplifying the way that developers need to build, because you're able to reuse your logic with essentially composable building blocks. And that lets you eliminate boilerplate from your code. It lets platform engineers build a component that slots in, that the application developer themselves don't have to manage. And one thing I really want to highlight here is that Wasm Native also works with Cloud Native. It has all of the existing Cloud Native technology integrations that you would expect. A common deployment strategy for WasmCloud actually is to be able to run on Kubernetes and orchestrate your applications with WasmCloud. When we compose applications, we're doing that in WasmCloud with open standards and common interfaces for platform capabilities. These can be swapped at runtime, allowing you to do upgrades for maintenance or even changing out the vendor entirely, because these APIs are at a high level. They're vendor agnostic. Now, we also allow you to write your own custom capabilities and interfaces, and we've had amazing amount of success, and we'll be doing later deep dives on our integrations with Postgres and Couchbase. One thing to understand when we're talking about building apps for WasmCloud is that we have a declarative application manifest. You might later today hear the word WDAM. That's what we're talking about there, the WebAssembly Application Deployment Manifest. And you can just think of that as like a Docker compose, but for Wasm. When we run WebAssembly applications, aka we're running them in a deployment, we allow you to run that across any device, server, or cloud. Now, this is something that's very, very different from other types of application architectures. It allows you to have a seamless distributed network that automatically load balances and fails over to available compute. We support vertical and horizontal auto-scaling with automatic failover, allowing you to reach this new level of reliability and fault-tolerant applications. Another added benefit here is that we do all of this routing local first. So if you're working in one region and there is a type of capability that's closer to you, we route to that first before reaching over across a different region. So in this scenario, we're talking about orchestrating Wasm applications. You know that Kubernetes is a container orchestrator, so you can at least think of WasmCloud as Kubernetes, but for Wasm. Another major feature of WasmCloud is that it's extendable at runtime. This is effectively a view of our stack for WasmCloud, where we support WebAssembly components that run in a Wasm sandbox. We have our Wasm host, which embeds a WebAssembly runtime called WasmTime. And then we have many different capability providers that are extendable at runtime. A single WebAssembly component has things that are called imports and exports. These are basically APIs. For imports, these are the things that my component needs to run, and my export are the things that my component provides. So in this case, I may be getting many different secure capabilities that are built into my host. These are often the WASI APIs that you see. And I can also import from extendable capabilities that can be swapped at runtime. Another amazing feature is that WebAssembly components themselves can build on top of each other, just like Lego blocks. And in this case, I can have one component who imports, aka depends on another component that exports an interface that it needs to run. So you might be thinking, why components? We already have containers. We have had amazing success with containers. So why do we need to go back to the drawing board on our fundamental piece of compute? And really, I think that part of the problem is the way that we manage with containers, we're bringing in the whole world. Whereas with WebAssembly components, we get down to exactly your business logic that is bundled into the app. And when we start back from first principles, we know that we need to use applications that are written in many different languages. We need to be able to support polyglot. And so we're able to do that with WebAssembly components, where one component written in Rust and another component written in Go can compose together and communicate over interfaces that are designed so that we can do interface-driven development. And they are also shared nothing linking, so each component is actually still isolated from each other. Now, you would think that with this level of isolation, there would be this massive performance cost, but that's really not the case. Going back to our latency numbers, now imagine two components that are composed together. In that case, they're actually able to run in the same process, which means when I communicate across that boundary, it happens in nanoseconds. And that is a major difference in Game Changer. Now, the way that we define these interfaces is with an IDL called WIT. It gives us some new capabilities that we don't have in OpenAPI or other IDL type technologies. And that really comes down to the interface types that we get out of the WebAssembly component model. And that is namely things like resources and streams. That gives us the ability to manage the lifetime and lifecycle of components as they're composed together, and in WasmCloud as they're distributed over the network. Later on, Brooks Townsend is going to give a deep dive on how we're able to use resources in a way that solves privacy and security concerns with our secrets. But more than anything, by using WebAssembly components as our primary unit of compute, we can see emerging types of patterns that are going to help platform engineering teams solve major problems that they're experiencing today. And I believe it's with the platform harness pattern. We're seeing that across many different enterprises that are adopting WasmCloud, where essentially they're building a golden template that all of their applications are able to compose with so that they create a single component that isolates and I would say wraps effectively all of the different logic that they need to be able to get their authentication, their secrets, all of the basic things that platform engineering teams are on the hook to provide, but they have the benefit of managing that themselves and maintaining a lifecycle separate from the application developers component that just composes their app. And once this application component is composed together, you can see that it doesn't expose those imports. It can now just run with the basic standard APIs. So what that gets us to is composable computing that can be distributed across the core and the data center, across edges and clouds. And that's going to be very powerful change in our industry. So to give you a taste of the art of possible, I'm going to give you a demonstration of a celestial and terrestrial mesh. Now, this is something that we are building in partnership with a number of different agencies that are interested in running WebAssembly in space. What I'm showing here on the screen is a world map with different data centers deployed in Azure and their connectivity over the internet. The job of this application is to identify whether or not something is a boat. So it's doing image classification once I upload an image. Imagine some satellite has just taken this photo and I need to image classify whether or not this was actually a ship. In this case, it decided that it was not a ship, so my prompt engineering here isn't amazing. It's pretty simple. Okay, this one is a ship. Let's do something else. Let's go right back up. Let me give it something that is definitely not a ship. And this is a member of our team. His name's Oscar. And he is not a boat. That is Oscar. And we'll do just one more boat before we're done, just so that I can know that here's a boat. That one's actually an AI generated boat, but it's real enough for an image classification system, exactly. So we'll dive a little bit more into the different pieces and parts that make this app real from the different capability providers as part of it, but I wanted to go ahead and introduce you to the use case. Now, this is a different view of showing essentially that global view that I showed a second ago, where we have a distributed compute mesh. And the use cases for this that we're seeing is actively growing. And today's methodologies just can't achieve it. Kubernetes itself and containers are not well suited for running in embedded devices on the edge, whereas WebAssembly is fantastic for that use case. And composing all of this together with the right enterprise-ready security and compliance controls, it makes WasmCloud ready for organizations to adopt. Now, you might be thinking this is new to you, but I just want you to let you know that this technology has actually already won. We're seeing it from Fastly and Cloudflare for serverless edge computing. It's in your TV. It's probably in my camera right now. It is definitely in Zoom that we're running. It is the way that we distribute our videos from Prime Video, Disney Plus, etc. It is taking over the cloud native landscape by storm as being the last plugin model that you'll ever need. So that means that Wasm has taken over the industry and you're using it everywhere. The future is here, it's just not evenly distributed. So I hope today you'll learn how Wasm Cloud is the picks and shovels that you need to bring Wasm into your enterprise. Thank you.